Okay, good afternoon, everyone. Let's continue with the root locus. Pole zero cancellation in the control design should only be done in the left half plane because we are not allowed to cancel unstable poles. Even in the left half plane, if we cancel poles which are kind of oscillating, we might run into trouble, especially when we have disturbances acting on our system. If we don't have disturbances, cancellations anywhere in the left half plane are usually fine. However, in most technical processes, you usually have disturbances. There are exceptions like robots and so on, right? Okay, so the next idea then would be, instead of canceling out the poles, we're going to shift them somewhere else. How does this actually work? And actually, we already have done this shifting of the poles, right? This was the slide which I couldn't get my mind on when we finished the lecture in the morning. So, oh, nope. This is how it works. Sorry for that. Let's get rid of this and draw it now. So far we used the zeros of our controller, right? We have a controller which looks like, for example, a PI controller, which looks like KPI, S plus mu, and S. And we said, okay, using this zero, we're going to cancel a pole of our system. Okay, so how did we do this? Let's say we have a simple PD1 system in the open loop, right? Okay. For that system, you could say, okay, I want to design a PI controller. I place my zero here above this pole, and I'm introducing a new pole, right? So this is the open loop then. What you see here in red and black is basically R of S times G of S, right? This is the open loop controller and plant. And now we said, okay, if we close the loop, we are relocating the remaining poles, basically. We could say, okay, we want to have a time constant of -1. So we are shifting this guy in the closed loop to -1, right? So this one would be T of S, right? This is what happens. So we already did this relocation, but just with the remaining poles or with the poles we newly introduced. Now we're going to assume what happens if we don't cancel these poles and place this zero somewhere else, right? You could say, okay, I have this, well, it's not a good picture here. Where do I have space? Let's say same picture as above, same PD1 system, right? You have this pole here, and you introduce a pole at 0 with your PI controller, and now instead of using that 0 to cancel a pole, you say, okay, why not placing the 0 here? Okay, when you close the loop, these two poles will get relocated. They will end up somewhere here in the left half plane, hopefully. The question is where, and this is what the root locus method is about, right? So the question now is, what influence does a 0 of our controller have if we don't use it to compensate a pole? We don't place the 0 above a pole, we place it anywhere we like in the pole 0 map. There must be a strategy, right? And the next slides are intended for us to figure out what's actually happening when we close the loop. Okay, let's take our example from before. It was this PD2 system, spring mass damper, where we had 4 over S squared plus 1.6 S plus 16. Remember, this can, for example, be a simple spring mass damper system. PD2 is a classical mechanical system where this guy simply oscillates, right? Okay, what did we say? We have poles of this guy. You solve after the Mitternachtsformel, you end up with minus 0.8 plus minus 3.92 I. So it's definitely going to oscillate. It's going to oscillate. This is confirmed if we compute the damping, which is 0.25. We have a static gain of 4 over 16, which is also, sorry, 0.2, wrong line. We have a static damping, which is 4 over 16, which is 0.25. And we have an eigenfrequency of 4. This is what we get out of this equation here, right? Okay, and now we're going to say, we're going to take this guy and we simply plug around a constant controller, a proportional controller, right? Okay, what happens is we take G of S, we introduce a proportional controller, basically as you have done in the espresso machine example in Simulink, and see what happens, right? Obviously, we know kind of qualitatively what happens. If we increase the gain, it might get more oscillations, it might get faster, we might move closer to the final value, right? So these are quantitative measures we kind of figured out with all we've done so far. But now we want to see that mathematically, right? We want to have an equation and see what's going on here. Okay, so that's why we simply compute compute the closed loop. So let's compute the closed loops, the complementary sensitivity. Let's compute R of Y, always the same stuff, right? So we have Kp times G of S over 1 plus Kp times G of S, right? So if you plug that in, you end up with 4Kp over S squared plus 1.6S plus 16 plus 4Kp. Okay? You should see that you're not gonna get 100% at the output if you let S go to 0, right? You have 4Kp over 16 plus 4Kp. So you move closer, the higher the gain is gonna be, but okay. So now we have closed loop equation similar to the espresso machine, right? Where we actually now said, okay, we want to have a damping, blah, blah, blah. Okay, this was basically a relocation of the poles. But now we want to see how the poles look like, okay? In dependence of this controller gain. Okay, we need to solve the Mitternachtsformel for this guy here. Then we get the poles, right? Okay, let's do this. Poles of the system, they end up, and I'm naming that P tilde because they are in the closed loop poles, right? Remember, these are the open loop, or these are the poles of our system. The closed loop, when we close this loop, we are changing the poles, and we want to see that now. If you change that, if you close the loop and calculate the poles now, you have this additional term here. You end up with an equation which looks like this. Minus 15.36 minus 4Kp. Okay, so far so good. So these are the poles depending on Kp, right? You can put in for Kp anything and some poles will result in the closed loop. For the espresso machine we said, okay, we want to have a damping of 0.9. So this 0.9 basically corresponds to one specific pole location, right? Obviously you have a line, but only for that system you will have one specific pole location. Okay, but let's discuss these poles. So what can we assume for Kp? Actually, we're not going to put Kp to anything. We are only going to put numbers which are bigger than 0. If you put Kp to 0, you don't have any controller, right? Because then the controller is doing nothing. You have a control error multiplied by 0. You will never get a command input. So we exclude 0. Why don't we put in negative numbers? Well, we always say we have a negative sign here. We want to have the control error multiplied by a certain gain. If you now basically say Kp can be negative, you're changing that sign to a plus here. So you're changing the sign from plus minus to minus plus. You're basically further destabilizing your system. So we're not going to do this. Okay, so we can fairly assume Kp for the feedback is always going to be positive because we want to have a negative feedback, right? We want to have the control error multiplied by -1, and we want to compensate that. If we say Kp can be negative, we are actually changing the sign in the loop, and we have a positive feedback, and we are destabilizing it. It's usually not a good idea. Usually, not always. So, okay, Kp can be positive, needs to be positive, is going to be positive. Okay. So, what happens if Kp is positive? So, if this Kp is positive, this guy here, right, minus 15 minus 4 times Kp is always going to be negative. I hope you agree. If this guy is always going to be negative, there will always be a complex solution of this one, right? Because for positive Kp, we cannot get the square root positive. That's why we're always going to end up with a complex solution. And what does that mean? If this square root is always going to be a complex solution, there will always be a complex solution. We will always oscillate. Okay? So, remember, our pole has an imaginary part and a real part. And this guy is always going to be complex. So this is always going to be your imaginary part, and you basically are not able to change the real part, right? The real part in your pole zero map will always be minus 0.8. So if you want to draw the pole zero map and say, okay, in the open loop, if we set Kp to 0, if you set this guy to 0 here, you're at this poles, right? So you are at minus 0.8 and roughly 4. Okay? So when you now say, I want to know Kp, and I don't want to know Kp. I'm setting Kp to different values. You know, you're not going to change. So there will be no movement to the left or right, because whatever you put in for Kp, this guy will not change. The real part will not change. It's always going to be minus 0.8. And the bigger, what we also know, the bigger we set Kp, the bigger is going to be the square root. So what we are actually doing, we are moving the poles to the outside, straight up and straight down. Okay? Okay, so this was my short version. Now I've written it down. Okay, so for positive Kp, the root always remains negative, right? And thus, the proportional feedback only affects the imaginary part, right? We are only affecting this guy here with Kp. The imaginary part gets larger the larger we make Kp, right? And the poles thus are further moving outwards. So this is 0.8 here. We are always going to stay at minus 0.8. And this is basically a side effect, we cannot increase the damping. The damping, basically, see, these are the damping lines. If you move just straight up, you're basically only able to decrease the damping because you're moving up. So, in this plot, and this plot is really important, please really see what's happening there. Because if you understand that plot, you basically understand the root locus. The blue one is our system, right? In system, I mean G of S, this guy here. These are the poles of G of S. Now, I'm setting my Kp to equal 1. Okay? I'm closing the loop. What's happening now, my closed loop, my T of S, so these define your closed loop. What I mean with that is you're simply doing, okay, you set in Kp and you have different values for that, right? And when you change that Kp, or for any Kp, you get a new pole location of this guy here, of the closed loop, of this T of S, right? So this is T of S. This is T of S, your closed loop transfer function, and these orange one are the poles of T of S for a Kp of 1. If you increase the gain to 5 here, you get new poles in the closed loop. So T of S has new poles. These are these ones. these ones. Yes, these ones. If you make your gain 10, you get to these ones. If you increase it further, you get to these ones. Okay? So it should get clear that for every different controller gain, you get a different pole location in the closed loop. Now, if you understand that, that's good. Now you do it for all different controller gains you can imagine, right? And what you end up is a root locus line. And this is the gray line here. So the gray line tells you, and actually the gray line continues to go outwards here for that example. This is called the root locus line. The root locus tells you, and this is where the name comes from, because you're making the roots of a polynomial, right? Where you can place your poles in a closed loop. And for our very simple PD2 systems, we can place the poles in a closed loop anywhere on this line, right? Depending on Kp. If you want to have the poles here, set your Kp to 10. You want to up here, where the green one is, set it to 20, okay? But you should see at this point, we cannot increase the damping for this one, right? We will not get a very nicely damped system. And this is where the zeros come into play. Remember when we talked about what are zeros doing in our system? They make our system faster and they increase the damping. So instead of a pure proportional controller, we will do the very same example now. We say a proportional differential controller. So we are having 1 0, right? Same thing as before, just we're going to change the controller. So I'm taking a little bit of more time here because this is crucial for the understanding of the rest of this root locus design. Okay, so now instead of a proportional controller, okay, let's say we have a PD controller, right? And a PD controller has a gain and it has a 0. Okay? And now we are not using this 0 to cancel anything. We are just leaving it there. Okay? Okay, let's compute again the closed loop. You know how the closed loop works. R of s times G of s over 1 plus R of s times G of s. If you plug in now your new controller and the very same system, you end up with the following PDT2 system. So I did it already, so I'm just giving you the result. It's pretty straightforward algebra, it's not that hard. We have s minus mu, and we have s squared plus 1.6 plus 4 kpd s plus 16. There's actually a bracket missing in the script somewhere. Minus 4 kpd tilde. I need to actually let me check that. Yeah, there's a bracket missing here, so there needs to be a bracket here. So if you have the filled version, please correct this. After 3 semesters, first time I'm seeing that. There needs to be the bracket here. Okay, so this is our new poles, and this time we have 2 free parameters, right? We are free to choose our controller gain, and we are free to choose our 0 here, right? This is the part of control design, right? We can select those guys. Okay, so where should we select it? We don't know yet. But let's see what happens with our poles. So if you calculate the poles of this guy, it's again going to be a little bit tedious, but not too much. You end up with 0.8 kpd. And actually I figured I need to correct this as well. Oh no, sorry for that. Plus 2 kpd tilde. There are brackets, plus, minus, and now a little bit long square root. 0.25 times 1.6 plus 4 kpd tilde minus 16 plus 4kpd tilde and times mu. And actually there's a mu here, sorry for that. Okay, so now actually our poles look a little bit more involved, right? Our controller gain shows up and also our zero shows up. So we can now influence, and this is the first thing here we should notice, you can influence the real part and the imaginary part. And actually it's not so clear what the real and imaginary part is, because now we cannot simply say, hey, this guy is going to be the imaginary part, because technically this guy can get positive, right? If you just make kpd large enough, this guy will get positive. The only negative thing here is this minus 16. Remember, our gain of the controller is going to be again positive only. So this first part is definitely going to be positive. This part too, because mu is this guy is negative because mu is negative. Okay, we need to place it in the left half plane. So, however, we can select k. Can we? Yes, we can select k that this gets positive. So it's not clear where our imaginary part is. Point is, with our gain k and our zero, we can now influence the real part here and the imaginary part. And the term under the root can get positive, so we can actually come up with two real poles. Remember, if you have a PD2 system and you have two real poles, you don't have any oscillation in there. Funny thing, or no, not funny, interesting thing is, however you select KPD, you will never be able to destabilize it. So you will never be able to make the poles have a positive real part. But it's just more like the side news. So compared to the example before, it's now a little bit harder to draw this line, right? Which points in the pole zero map we can hit, right? Because I mean, this is a simple system. It's a PT2 system with a PD controller, so pretty standard. Although the poles, they are already looking a little bit nasty. So this is why in the pole with this root locus, you're basically use computer-aided tools which draw you these lines, right? It would not make sense yet now to draw the points for every KP and every mu, right? Okay, so. And this is actually how it looks like. I fixed now our 0 to -1. This one is here, right? This is the controller. And now I'm changing my gain here. And for the different gains here, you get different locations, right? So again, the blue one is just the open loop. So for this one, KPD is basically 0. You're left with the system here. Right? And whatever gain you select gives you a different location of the poles. So you select it to 1, you have these locations, you make it bigger, and suddenly you see you get to the point roughly here. So the gain is somewhere between 2 and 2.5, where you hit the point where the square root is not negative anymore. It will get 0 at first, then you are at this point, and then when you increase the gain further, your square root gets positive, and you're basically lying now on the real axis with both poles, right? However, with this line, with the gray line, now you see you never get to the right half plane. This is not always true. This is just this example, right? Again, these points here are the pole location of the closed loop for specific gains. If you do this arbitrarily often for all the gains you can imagine, 1, 1.1, 1.2, you end up with this gray line. So this gray line is the root locus, and it describes you which points you can reach by changing the proportional feedback. So if you change the proportional feedback, so the question now is, okay, That's good to know, but our controller has 2 degrees of freedom, right? We also can change the 0, and indeed you can. If you change that 0, let's say to -4, the whole line will change, right? But the methodology, the root locus methodology, what it does is the following. You always draw the lines only for the gain, and if you decide, I don't like that curve, I want to have it more to the left, then you add zeros or poles to your controller and draw the line again. And then you see what can I reach with this controller, right? So it's a kind of iterative process, but we will see to make it a little bit more structured. So important takeaway here is really the gray line here. This is the root locus curve. The root locus tells you which points in the closed loop of my poles can I reach by changing the controller gain. Okay? So let's get back to our example. And our example was this PT2 system where we desired a damping of 0.9 and a frequency of 11. And we said we are not going to cancel the poles, but we're going to introduce a PI controller to do so. So I did that using MATLAB. So if you do that, you end up now with a closed loop. Actually, it's just a PD controller. So you have your 0 here and you have the gain here, right? So, and if you place your 0 to -5.7 and your KP 4.4, you basically get to the same result as we had with the pole 0 cancellation, right? So that was my design constraint. And the crucial part here is now that the closed loop looks pretty much the same. However, remember when we looked at the disturbance sensitivity, we said, okay, the problem is if we cancel out these lowly damped poles, they're going to show up in the disturbance sensitivity. And here I'm showing you now the new disturbance sensitivity with a PD controller. And you should see now they are really, if you plug in the numbers here, you see that we actually moved these 2 poles and did not cancel them, right? So now we actively moved these lowly damped poles to a region where they are very well damped instead of canceling them and introducing new ones, right? This was the thing we did with the cancellation part last in the morning. So, bad news, we still did not achieve the same performance as we had before because in the example where we canceled it, we introduced an integral controller. And one of you, remember, I had the questions where to put the parasitic delay of the PID controller, right? So the problem now is if you take the PD2 system and a PID T1 controller, you're having now 4 poles. And it's not so easy to calculate them on paper anymore. And that's why I did it in advance with MATLAB. And now I can show you the comparison of these 2. But you find everything on the server in MATLAB if you like to look at it. So on the left-hand side, you see the results from the pole 0 cancellation example. So this is the pole 0 cancellation. Okay, here we said, okay, if we cancel it, we will get a very nice complementary sensitivity function. It's going to be fast and it's going to be accurate, but we will have a disturbance sensitivity which does not look so good. It will get excited because these poles we cancel will still show up in the disturbance sensitivity. And this is what you see here. Okay? This is what I try to emphasize here. These lowly damped poles only show up in here. Okay, and now with the root locus, this guy is very much flattened. So what we now did, we introduced a PID controller. Again, having 4 poles because 2 of our systems and 2 of our PID T1 controller is 4 poles. They are all going to show up, and we kind of got the, this is a smiley, right? So, okay, we got the disturbance sensitivity down. However, now we are kind of, I'm not sure if we won a lot, right? Because you could say, okay, the disturbance sensitivity got down. It's about 0.05, while this one was 0.1, but we got a lot of overshoot here, right? So this actually got worse. And there you should see control is always going to be a trade-off between things, right? You can never, barely never make everything perfect, unfortunately. However, we will get back to that example in probably 2 weeks, and I will show you that the right case is actually better. This case is actually better than this one. Why? Simple fact. The left one is the disturbance excites our system and we get a lot of oscillation in, right? While the pilot is inputting something, the blue line, it looks pretty nice. Here, the disturbance is nearly fully mitigated. We don't have any effect of, well, a little bit, but not too much, effect of the disturbance in our loop. However, when the pilot commands something, he gets a lot of overshoot. And this overshoot actually does not come from the poles, right? Because they are all very well damped. This comes from the zeros, because we have 2 zeros in the system from our PID controller. But why should this on the right-hand side be better than on the left-hand side? Because we still can improve the right-hand side, while we cannot improve the left-hand side. So you might ask now, why? Simple answer is what I just said. The blue one is results from a command input, right? When the pilot, let's think of a car. When the pilot is doing something, he gets a lot of overshoot. However, we know when the pilot is doing something. We can measure that, right? We can measure, or usually in digital control systems, X by wire, for example, when the driver makes this on the steering wheel, the computer knows that, right? So you can change that signal and you can make that thing better. However, on the left-hand side, this is perfect. No improvement there, but you cannot change this one because you don't know the disturbance. You don't know the wind. Now you could say, okay, I can measure the wind. Yes, but let me tell you, these measurements are pretty bad and it's pretty expensive. You need a radar system, for example. I mean, they tried doing with aircraft, but it's still not pretty feasible, right? You can, but it's expensive, it's heavy, actually all what you don't want as a customer, right? So bottom line is, as we still can influence that signal here, because the system is excited by our pilot, by our user, we can pre-modify it with a pre-filter. While we cannot change this guy because it's a simple disturbance. Okay. So far to that, but now the next thing is we need to dig deeper into the root locus plots, right? At this point, I'm going to take a drink. At this point, you should understand that you have, and this is really important, right? Because sometimes this is hard to overcome in your mind, right? Because you need to understand this to understand the root locus. If you have a controller, you change that gain, you're basically changing the dynamics of your system. And this is actually what the idea of the first and second lab exercise was about. Obviously, it was also about that you learn some Simulink and MATLAB and get up to speed on that. But it was also to understand when I change my controller, my time signals change. Why do the time signals change? Because I'm changing the dynamics of the system. I'm changing the closed loop ODE, so to say. I'm changing the closed loop poles. I'm moving the dynamics around where I want them to be, right? Otherwise, you would not be able to stabilize a rocket, for example, or an aircraft. You're changing these eigendynamics. Okay, the question now is, we can have very complicated controllers with zeros, with integrators. Is there a systematic behind to change that lines where my closed loop poles are going to be systematically, that I can make up a strategy of that? So the strategy will be, oh, I need some more damping. Okay, I add a 0 there and there, right? So this is where we want to get to, but this will require some considerations. So let's sum up where we are. As seen, the poles and zeros influence the path the system poles take independence of the gain, right? So that means simply the closed loop poles change when we change the controller gain, but they are also changing its location, or when we introduce zeros and poles into the controller, right? And the good news now is how these lines are changing, these root locus lines. There we can actually, I can present you a fixed number of rules how these poles are moving around. And you will see it's not that hard, you just need to do it a couple of times, then you get used to it. When you read books, the number varies. I've read books, there are only 2 rules. I've read books, there are 20 rules. You can always make it complicated. I will get around with around 8 rules, right? This is, this is enough to understand what the root locus plot is, I think. But you don't need to learn them by heart. You can always look them up. But you will see they are not, you need to remember 2 or 3 rules and the others kind of come naturally. Okay, and these curves are actually called the root locus plots. And the method for controller design is known as the root locus method. In German, it's Wurzelortskurve, Wurzelortskurvenverfahren. So, root locus plot im Englischen ist im Deutschen die Wurzelortskurve. And the root locus method ist das Wurzelortskurveverfahren. Warum? Ich sage es jetzt mal noch auf Deutsch, weil das ist immer wieder, gibt es so ein bisschen Missverständnis, warum heißt es so? Gut, Wurzelort, ne? Die Wurzel, mit der Wurzel ist gemeint, die Nullstellen des Polynoms im Nenner, ne? Das sind die Wurzeln des Polynoms. Und der Ort kommt halt, weil eben wir eine Abhängigkeit von unserem Reglergain haben. Ja? Das heißt, der Wurzelort der Abhängigkeit ist vom Regler. Ne? So, daher kommt der Name Wurzelortskurve ein bisschen. Ja. Root Locus Plot, Wurzelortskurve. Ja, nur damit das klar ist. Weil ich war einmal im Praktikum und da habe ich gefragt, haben Sie Wurzelortskurve gemacht? Und dann hieß es, nein, wir kennen nur Root Locus Plot. Na gut, ist das Gleiche. Also, dass Sie beides mal gehört haben, jetzt diese deutsche Erklärung dazu. Gut. Ich habe noch etwas für, Entschuldigung, ich muss, I have another explanation which is of the root locus curve, which is a little bit more, let's say, hardware driven. Okay, because I think this root locus sometimes, needs some time to digest in the brain. So I thought the next slide should help on that, what the root locus curve is for those who have trouble with. Okay, let's say we have that spring mass damper system, right? And we know we can come up with a transfer function of the second order system, where this system is described by a damping coefficient and an eigenfrequency, right? Okay, I think that should be clear. Note that this big D, capital B, is not the damping coefficient you have directly have in the mechanical system, because you have D is D over M, I think, or something. So there, it's a decrease. It's not a typo of my side. D is really not this D here. However, we know this system here is roughly a PT2 system and can be described by this PT2 transfer function, right? Okay. So, I hope you agree with me. If you change the damping here, you will change also the D term, the damping term here, right? If you change the spring, you will also change the eigenfrequency and so on. Okay. And let's say you build up that spring mass damper system and you're not happy. You think, okay, it's oscillating too much. You go to the hardware store and you buy a new one. Say, This is a good one. This is better damped, right? I mean, this is actually a classical system, how you would model like a wheel on a car, right? Like a damping system. Okay, I don't know, Punto is oscillating too much. I'm buying me a better damper into my car. Okay, you plugged it in and you figure, oh, okay, I was a little bit too positive. Now it's has a too big damping. Okay, you go to the store, buy another one, and hopefully at some point you will converge to one you like. What you actually did is you always change the damping in your system. In your transfer function, you change the numerator, you change the eigendynamics, right? And the root locus curve is actually nothing but that, right? You going to the shop and buying different dampers, you're basically moving these system dynamics around for a lot of different points. You start here, you go to the shop, buy a very hard damper, you end up here. You see, okay, it's very good damp, but it's too slow, so I need to go back and buy another one. So you end up with a lot of dampers, and what the root locus curve is, it basically gives you a line for all the dampers you can buy, right? So if you, instead of these discrete points, you just draw a line through all the points, and you will see, okay, by just changing this damping here, I'm actually changing the location in the pole zero map. You could say now, okay, what does changing a damper in my mechanical system have to do with actually a control loop where I'm closing the loop? Well, a control system is doing the very same thing. It changes, for example, if you have the right feedback, it actually just changes your damper. You can make a different controller which just changes your spring, right? A control system is just an artificial system which you plug on a computer because you don't want to go to the hardware store. You plug it on a computer and let the computer do the job, right? You're artificially changing this with electronic signals. You're changing your damper via a control loop. It's the very same thing, and this is why I think this interpretation is actually should be pretty helpful if you still struggle what the root locus curve is. Okay. Yeah, what time do we have? 4 o'clock, so we still got 45 minutes left. Okay, I would actually jump right into the rules, how we actually draw these root locus plots, right? I told you there are 8 rules, and we're going to go through them step by step, right? I'm going to show you 8 rules, and then we're actually going to do some examples on that. Probably not today, so that's going to be, yeah, probably not today. No, probably not. But we start with the 8 rules, and you see it's really not that hard. And then we're going to practice it. I think I've got 10 examples on that. Okay, so where are we? We know that the feedback loop changes our dynamics, and we now want to know where are these lines, these famous root locus lines, right? And how many are there? Is there only one? Are there arbitrary many? Where do they go? Where do they start, right? These are the questions of the 8 rules I'm going to present you. They are hopefully answered them. Okay. So, sorry, I just need to, it's actually getting pretty humid here because of the rain. So, actually, you can directly design a controller by doing the root locus design, right? So what you're doing is you draw the root locus line, you select the point you like, and then you compute the gain. And you actually can do this on paper. And this is actually why this method is actually pretty old, right? So as for the PD2 example, you saw we actually were just drawing them on paper, and you would say, okay, I like that point, let's calculate back the gain. To be fair, nobody does that today anymore, because while we probably need for a root locus curve, let's say, I don't know, 5 minutes or 10 minutes or 50 minutes to draw, a computer needs not even a second to draw. So it's much more efficient to use, for example, MATLAB or Python when you like to draw these lines, right? So to really apply this method, we are relying on software tool. So now you could ask, why should we still learn this? Well, we still need to learn this because we don't want to kind of try and error infinitively, right? You still need to understand, okay, my system does not look like, and most of the time, the point you want to place your poles in a closed loop are not going to be on a root locus. So you need to change the controller. And to understand how to change the controller, you need to understand the root locus rules, right? You need to understand, if you place a 0 somewhere, what happens to my curve, right? If we don't understand this, we simply open MATLAB and it's going to be a nightmare because we don't know what we're doing, right? This is why you have to still learn these rules, although we don't have to do all the designs on paper, right? But we need to understand where it comes from. Okay. So where I actually screwed up my animation style. I think when I changed to the new Hochschule logo, all my animations got broken. I'm gonna fix that, I think. Okay, so first thing we always need to do is we need to think about what is the root locus telling us. Well, the root locus tells us something about the pole locations in a closed loop for only proportional feedback, right? So, okay, how do we get the closed loop poles? That's actually pretty easy because we only need to set the numerator to 0, right? So this should not come of any surprise at this point. So this guy here gives you the closed loop poles. Okay, so much to the animations. Okay, so the point is, and this is really important here, it's always going to be a constant gain here, right? Which we can change. So now you could say, okay, what's going on here? Because we saw a proportional controller is not always sufficient. Just think of steady state accuracy. You need an integrator. If we want to speed it up, you need a differential term. Yes, that's true, but you still draw the lines only for the proportional gain. When you say, okay, I like to have an integrator, then you stick that integrator to the plant. And for that new plant, for that artificial plant, which basically is your original system multiplied with the dynamics of the controller, you're drawing the root locus, right? The root locus curve, however, always shows you the points which you can reach only with proportional feedback. But this is not a restriction, right? Because you can still put any dynamics you like in your controller. You just need to move it. You need to move it to the system for a while because you again want to know which points to reach with proportional gain. Okay. Otherwise, a two-dimensional working style would not work because you basically think of a PID controller, you need a three-dimensional graph then, so this is not going to work. So what you basically do is you're restricting yourself to this one controller gain, and all the other elements you plug in here. Okay, so I will show you a quick trick how to compute actually to compute this guy, because you should realize that this is a rational function, right? G of s is a polynomial over a polynomial, so this is not that easy to solve. Okay, you can split up your G of s simply in, and we did it when we introduced the polynomial form. You can split up your G of s in a C of s because of Zähler, and then the denominator n of s, right? Okay, so and then you multiply this guy by n of s, right? And this is actually always going to work. And this is actually a pretty simple mathematical computation, but it actually shortens some calculation you need to do pretty quickly, because your closed loop poles are always going to look like this. You need your zeros of your system set multiplied by Kp, and you take your open loop poles, which are on the left hand side. And this is actually why I'm actually solving those double fractions so quick, because I'm always doing that in my head. So I give you an example how this works. Bottom line is, you want to know the closed loop poles, right, of a transfer function. So you want to know, I give you a transfer function, I give you a controller gain, and you want to know where are the closed loop poles, right? You always can compute T of S, do the double fractions, and go on, right? But there's this way is much faster. Let's show. So let's say we have a G of S of 5. So we have 0.5 over S plus 3 out of 5. And we want to close the loop and put around a controller gain Kp. This Kp can be any number now, right? Could be a question, right? I give you a number, I give you Kp of 5, what are the closed loop poles? Okay, technically, as we have learned it, we would go the following. We would say, okay, we go from here to here, which is T of S is nothing but, okay, going directly, 0.5 Kp over S plus 3 divided by 1 plus 0.5 Kp over S plus 3. Then you, what is going on? You solve the double fraction, it's going to be 0.5 Kp over, this goes up as plus 3 plus 0.5 Kp. Done, right? The characteristic equation now is only the denominator plus 0.5 Kp equals 0. Okay. How many steps? 1, 2, 3. Okay. Decently fast. Now, what this says here, okay, just take the open loop poles, S plus 3 plus Kp times the zeros. Okay, we don't have any zeros, 0.5 equals 0, right? Done. So I hope you could see that this was shorter, right? This is already your characteristic equation if you use that. And this simply becomes of the fact that we split up our G of S in a numerator and a denominator. Okay. Okay, why is this important? Well, we always want to end up with this equation. We need to check our characteristic equation. What is our controller gain doing to our poles, right? We are interested in that. What's happening here? Here, if we say, okay, Kp is always going to be positive, we actually move our pole from -3 to the left, right? So if you would draw, what's going on? If you would draw the locus curve, you first start with the open loop pole at -3. If you increase Kp, well, this guy moves to the left, right? You move it further to the negative, you stabilize it basically. What? So, okay. So we know now that if we solve the characteristic equation, we're solving the roots of this equation, which correspond now to our new poles of the system, right? When we solve this characteristic equation, we get the poles of the closed loop, right? And again, as I know I've said this a couple of times today, but this is really crucial to understand. If we change the controller gain Kp, we are basically changing the location of the poles, right, in a closed loop. This is ultimately what control is about. You want to change the dynamics, right? You want to make your system faster, more stable, less damped, and so on, right? This is what control is about. you're changing the dynamics of your system. Okay, the question now for us is how? How do the poles move exactly if we change Kp? Where do they go? And here I'm going to show you 8 relevant rules you need to consider. And if you have kind of thought about these rules, you will immediately know where these poles are going. And usually it's kind of, pretty straightforward where they are going. Okay. These 8 rules will show you how they are moving, and we're going to jump right into it. Let's start with rule number 1. We're probably going to do 4 of those today, and let's see. Yeah, let's see. Okay. So, first question, how many curves do we actually have, right? So, how many root locus curves? I've shown you this PD1 examples, only was 1 curve. And actually, the number of curves we have is determined only by the number of poles or zeros. And remember here, it's an or here. Whichever number is greater. So you just need to count the poles and you need to count the zeros, and we define it by NP and Nmu. And then you say, okay, I know how many curves are there. So PD1, right? This is a PT1. It has 1 pole and 0 zeros, which is larger, so the maximum is definitely 1, so we have 1 curve. If you look at the pole 0 map, I draw it in MATLAB now, it's exactly this example. We have 1 curve, right? This guy here, 1. Okay, another example. This is, what is this? It's PD2T3 system. Yeah, okay, doesn't matter. We have 3 poles and we have 2 zeros. Obviously, 3 is bigger than 2, so we should end up with 3 curves. 1, 2, 3. Okay. So, the good news is we actually don't need to talk about the maximum. We can always just count the poles, because remember, a system which has more zeros than poles does not physically exist, right? Also, when this number is the same, it's kind of problematic, right? In physics, it doesn't exist. However, it does exist when we do coding. It exists in filter stuff, what you probably learned in EE. So, however, if it's the same thing, we still can look only at the poles. So actually, this rule number 1 actually simplifies to the fact that you only need to count the number of poles, right? When you know the number of poles, for our systems we have as engineers, you already know how many lines, how many root locus curves you have. 1, 2, 3. Because we have 3 poles, we've got 1 pole, we've got 1 curve. Okay? Okay, next rule, number 2. And this rule is actually quite important. The poles move to zeros with an increase in controller gain. Right? Okay. That means I have a 0, I have a pole, and this guy kind of moves in this 0 when we increase the gain. Why is that? Well, let's see. This is the characteristic equation from 2 slides before, right? This is the characteristic equation. If you look at that, and now let's say we're going to put Kp to 0. Putting Kp to 0, this is straightforward, right? What does Kp to 0 mean? When you put your controller to 0, you don't have any controller, right? When you don't have any controller, your system has the poles it just has. You're not changing them, right? Remember, your system is G of S. Your system is G of S, which is some numerator over the denominator. And if you don't have any controller, this is all what you have, right? So if you set your controller to 0, you are left with the open loop poles, right? Meaning that this is actually your starting point. Remember when I've shown you the examples, the root locus examples for the PD2 system where they moved up and down, just straight up, we also said, okay, if we don't have a controller, these are the poles of the open loop. Okay, so now let's say what happens if we move Kp to infinity. If we move Kp to infinity, this guy becomes predominating in the equation, and this n here is much, much smaller than this guy here. So what we are left with is Kp times z of s equals 0. If you divide that by Kp, you are left with z of s equals 0. So that means for very, very, very large gains, your closed loop poles move into the zeros. And what happens if you move them into the zeros? They are basically cancelled, right? So another interpretation would be if you move the gain very high, you make your system very fast, right? Because you have a perfect cancellation there. But not always. Because what happens if we have more poles than zeros? Then there is not a pole, then there is not a 0 for every pole, right? Because every pole can just go to 1 0. But that comes next. Okay, important here, the poles go towards the zeros when we increase the controller gain, and they're going to end up there. What happens with all the others? They're going to end up in infinity. Okay, but let's do an example. So this is a system where we have 1, 2, 3 poles and we have 3 zeros. So we should somehow have 3 lines, right? And the characteristic equation is again n of s plus, and this needs to be Kp, sorry for that, this is still old. As I told you, I kind of tried to get it a little bit more uniform this semester. Kp times z of s equals 0, right? Z of s over n of s. Okay, and now if you draw the root locus plot, we are actually, this guy moves into that 0 and these two poles move into these two 0. The matter of fact is you're actually having an unstable system here, but this is just a side note at this point. Okay? Obviously, if you put Kp to 0, you only have the open loop poles. You only have these guys here. And then if you increase the gain, you're moving in these directions. So this is now the case, what happens when you have the same number of zeros and poles, because every pole can end up at 1 0. If you don't have any poles, if you don't have that much zeros, we will see what happens then. They go to infinity. And I will tell you a pretty bad joke to remember that. I swear you will remember that bad joke because I did it now for 20 years. You will remember that bad joke too, but it helps. So it's again, I will tell you. Okay, so rule number 3, and this is kind of, I mean, when you understand everything so far, this should be obvious, right? Yeah. In case roots are complex, they appear in conjugate complex pairs, right? The solutions are going to be conjugate complex if they are complex, so to say. So this guy here has, or looks like this, right? If you solve that, it is a pole at -10. These are the zeros, and if you solve this guy here, you end up with a root locus with 2 poles which are kind of mirrored around the x-axis, right? The real part is the same. This comes from the Mitternachtsformel, right? That the real part needs to be the same if they're complex. Whenever you end up with something like this, it's going to be wrong, right? This cannot happen because there needs to be a conjugate complex pole pair always. To be fair, this picture, I draw it myself, right? This is basically comes from MATLAB. This comes from Photoshop. So this, you cannot even construct this left case in MATLAB. It will not work, right? So yeah. Okay. Rule number 4. There is no crossing of a root locus curve over itself, right? So let's take that example from before with the 3 poles and 3 zeros. We said, okay, this is how it looks like. They can cross over each other, right? This is okay, but they never can cross over itself or themselves, right? So the green line crosses here over itself. This cannot happen physically, right? So you really see, I mean, rule number 3 should be obvious. Rule number 4, it's also not that hard, right? There's no crossing over each other. These rule number 3 and 4 are more like to double check your results, right? When you say, oh, I'm crossing it, cannot happen. Okay, I did something wrong there. Again, they can cross over each other sometimes, but actually this is rare. Okay, so the next rule, and actually we're getting through pretty fast, so probably get to the end. Rule number 5 is actually pretty important. So this is one of the rules you actually can start with when you have the task to draw a root locus curve. Okay, so we're gonna take some time with this one. And this is the so-called real axis condition. A part of the real axis belongs to one root locus curve if and only if there is an odd number of poles plus zeros on its right side. Okay, this is a little bit long, but it's actually pretty easy. Let's take this example from before. It looks like this. And it really tells you, rule number 5 tells you which part of the x-axis, right? So we're talking about the x-axis, only this guy here. Which part of the x-axis is part of the root locus plot of a root locus curve? Is it this one? Is it this one? Is it this one? Right? You need to know that to be able to draw that nicely. And the rule says a part of the real axis belongs to the root locus curve, or actually to one root locus curve, if and only if there is an odd number, so eine ungerade Zahl of poles plus zeros on its right-hand side. So take this point, right-hand side, there are zeros. It's not an odd number. So this here should not belong to the root locus curve, right? Take this point here. On the right-hand side, there is 1. So maybe, no, not maybe, this part here should belong to the root locus curve. This guy here, 1, 2, 3, 4. Also, this should not, and so on, right? I think I have some animation this time going on here. Let's see. Yeah, okay, this is what happens. Right-hand side of this one is 0. It's not it's an equal number, so it's, yeah. Here you exactly have 1 on the right-hand side until you hit that point. Here you got 4, does not belong. Here you got 5, this belongs. And so on. This is, I think it's a very simple rule. You need to do it once or twice. It's really not that hard. And actually, if you look at the root locus curve, it's exactly looking like this, no? Right? So this area belongs to the root locus curve, and this one too. And my pen is again playing tricks with me. Okay. Please note that this holds for negative feedback. Whenever you come to the point, and actually this happens sometimes in flight control, if you have positive feedback, the rule changes. You then need to look to the left-hand side, or you look to the right-hand side for even numbers, not odd numbers, right? It's the same. Okay, so this really holds for negative feedback. Okay. 3 more rules, then we are done. The root locus curve always leave and enter the real axis with plus minus 90 degrees. Okay. So let's say we have a PD5 system where we have poles 1, 2, 3, 4, 5, or -1, -2, -3, -4, -5, and we're going to take a look at this system. And a matter of fact is that these poles basically split up here, and they leave the real exit at plus minus 90 degrees, right? It's always going to be like that. Whenever they hit each other, they're going to leave, one goes up, one goes down, and happens by 90 degrees. Okay. There is an additional rule which I don't actually present to you because it takes some heavy mathematics. No, not so heavy, but it's kind of nasty. So I don't actually want to do it. Namely, this rule tells you where they are actually leaving, right? You can actually determine that point here where this kind of curves leave the x-axis. Matter of fact, here it's in the middle, but here it's not in the middle. See, so you could additionally compute it, but we won't do that. So if you get that and you draw it here or here, it's totally fine, right? So for me, it's just important that you understand, okay, they leave with 90 degrees and they go somewhere. Okay, and now this important rule, which I talked about before. If there are more poles than zeros, and this is actually will be the case very often for physical systems, the difference in the number, so the number of poles minus the number of zeros, rule locus curve go to infinity, right? Take the same example as before. We have no zeros. We've got 5 poles. 5 minus 0, the absolute value is 5. So 5 curves. We have 5 curves, and all 5 curves go to infinity. What you see here, right? They continue going to infinity. The poles need to go to the zeros. When you have more poles, they go to infinity. Yeah, but now the question is, at what angle do they go to infinity? So I'm done with the joke, right? Okay. So this is the explanation of why they go to infinity, because at infinity, mathematically, there are also zeros. But because they are at infinity, they are so fast that we are actually ignoring them, right? This is the case. Okay, so only 8 viewers. So okay, I guess the joke was too bad. How do they go to infinity? Well, they go to infinity along asymptotes, right? And the question now is, how do we find these asymptotes? The asymptotes, they all have a center of gravity. In German, you would say, these asymptotes haben einen Schwerpunkt. Yeah? In English, you say they have a common centroid. So you don't use center of gravity in English, it's centroid. But it's one common point where all the asymptotes meet. And we actually can compute this point. You basically only need to take the poles and subtract all the zeros, right? So you're adding up all the poles and you subtract all the zeros and you divide by the difference in number of poles minus number of zeros. Actually, this equation gets a little bit simpler because if you add a conjugate complex pole pair, let's say you have -1 plus minus e, you add those together, it's going to be -2. So all the complex parts, the imaginary parts, they're gonna cancel out because it's always going to be plus minus the same value. So you only need to add the real parts. And this is what's here. Take the real parts of the poles, subtract the real parts of the zeros, divide through the difference between the numbers of those two. You get the centroid on the real axis. And then in the second step, you compute the angles. And here, actually, it looks kind of, it does not look too hard. But what it says here, you let K, this guy here, go from 0 to NP minus mu minus 1, right? So you subtract NP minus the number of poles minus the number of the zeros and subtract one more, and you plug it in here. And then you divide it through the difference in the number of poles minus zeros, right? So this is the difference. What's crucial here? That's a weird joke. Okay, good. At least if a woman says that. Okay, nice joke. Okay, yeah. I lost my what I wanted to say now. It's always here when it comes to that joke, right? So, okay. What's important here on that equation is that it does not depend on the location on the poles, right? Does not depend on the location of the poles. So whatever location you have, it's only what counts is the numbers. So when you have two, if you have 2 poles and no zeros, it's going to be 2 here. And you will see this is actually pretty easy, these asymptotes, because you don't have so many options, right? Because they are independent of the location of the poles. They are only depending on the number of the poles and zeros. They're always going to look the same. So if you have np minus n mu equal 1, this is going to be 180 degrees. If this guy is going to be 2, it's going to be 90 degrees. If it's going to be 3, it's going to be 60 degrees, I think. Yeah. If it's going to be 4, it's going to be 45. And this is always going to be the same. And as I promised you, we're going to do, I don't know, 10 examples. And after that, you will know that you don't have that much options how the asymptotes look like. So what time is it? Okay. Should we start? We'll probably do 2 examples to get a little bit of practice and do the rest next time. So I'm still laughing about the jokes. Okay, so we have a PD2 system. Or yeah, it's actually still the rule number 8. Okay, let's do it. Okay, so rule number 8. The centroid, this equation here, let's go back, it's this one here, says we need to add up the real parts and of the poles and subtract the real parts of the zeros. Okay, so this system here, I write it out once, right? It's basically s plus 1 times s plus 2, right? Okay, only thing which can go wrong is that you need to be aware of that the poles are negative, right? Okay, so we take the poles, the real part of the poles, minus 1. We add minus 2. We subtract the real parts of the zeros. We don't have any zeros. And we divide over the number of poles minus the number of zeros. And this should be roughly minus 1.5. Okay? Rule number 1 says we need to have 2 curves because we have 2 poles, right? We have a delta, so we have 2 more poles than zeros. So 2 poles need to go to infinity, sorry. And we're going to apply the rule on the right-hand side. This does not correspond to the root locus, this always, but here in this green one, we have, if you would take this point here on your right, you have 1 pole, so it's an uneven, an odd number, sorry, and this is why this line needs to belong to the root locus curve, right? Okay, so, and the angles, here are the angles, basically this equation here, so we need to go from 0 to 1, because we've got 2 poles, minus 0 minus 1 is 1. And when you solve that, you end up with the angles of pi over 2, which is basically 90 degrees, and 3 pi over 2, which is 270 degrees or minus 90, right? So 90 degrees or and plus 270, which is equal minus 90, right? Okay. So, and that's it. So we know this is part of the root locus curve, so they can only go left and right. They're going to meet here. This is the centroid, right? Minus 1.5. And we've got in that centroid, we actually have 2 asymptotes which go up straight here. we know they're going to meet here, and the curve's going to go straight up and straight down. Right? Okay, these are the 8 rules, and now it's just a matter of exercising those rules. And I actually would say, let's see, okay, not so many. 5 more examples, and I would say you take the not filled slides and you try those at home, because I think that's a good exercise. And then we do the remainder of the 5 examples next time together, and we'll see if everything worked out. Okay, then we can finish now 5 minutes early, I think. So that's it for the root locus rules. We will still need some more time for the root locus next time, because we still don't know, after knowing the rules, how we design a controller. But we will go into that next time, because ultimately we don't want to only draw the lines. We want to come up with a controller gain and say, okay, we need that controller gain to place our poles at the desired location. So the usual strategy is, I give you a system, you draw the poles, and now you say, okay, from an engineering point, it makes sense to place the poles there or there. We will talk about criteria which makes sense. And then you need to select the controller in a way that your root locus curves go through these points you like to have. When they do, you can compute the gains, and then you can compute the gain. It's only one gain to place the poles at this desired point. So this would be the control design strategy, right? You have an open loop, it has poles, and you as an engineer have the desired poles somewhere in mind where you want to place those poles in a closed loop. Now you need to find a strategy, but for that we need to understand how are these root locus curves actually looking like, how they are developing when we have poles and zeros. But with these eight rules, we have a profound understanding and we have a good basis, and it's actually enough to draw those lines. Servus.